We will continue to explore the temperature-dependent sex determination and the sex ratio, but with a little different subject. We will need it after the thermal reaction norm of development, how we can model the development of embryo, what the metrics we can use, and what model we can use. The subject of this video is the development, how we can model the development of a turtle. The development is a change from the zygote formation to the peeping when the hatchling goes out of the egg, or in the specific case of marine turtles, when the hatchling goes out of the sand, depending on field constraint. The development has been historically described using table of development and stages. A stage is a distinct phase of the formation of an embryo characterized by specific morphological cellular change, apparition of organ, or some specific period of development. Here I show some very nice picture of development of leatherback by Renu and colleagues. The stages are discrete period of development, but from a modelical point of view, it is easier to work with continuous criteria. The continuous criteria that we can use can be the time since egg laying, the mass of embryo without the vitellus, of course. Several organs have been used in literature, for example, the diameter of the eye, the total embryo length, or the straight carapace length, SCL. It is also possible to model the progress of development from 0 at egg laying to 1 at hatching. This graph represents the size of embryo according to the developmental time at 3 different incubation conditions, 2 constant temperature and 1 from field. We have seen several metrics, but what is the best metric? What metric we should use? Time is clearly not a good metric because the rate of growth and then the time from egg laying to hatching depends on incubation temperature. We cannot anticipate when it will stop, so working with time is very complicated. Mass is highly dependent on the content of water, and it can decrease during development. It is very complicated to model such metrics that can grow and decrease. Egg diameter is difficult to measure. You can make a huge error without a good binocular microscope. Total embryo length is also difficult to measure because the round shape of embryo, and it's not a very practical measure. Straight carapace length is easy to measure, but it does not exist at very young stage, and for a very young stage we must use equivalent size of SCL, straight carapace length. The progress of development is easy to measure at the beginning and end, because it will be 0 and 1, but at intermediate development we don't have easy way to say that we are at the middle of the development. We will see this later. Then we will use, and in literature, the 2 last have been used. We will explore both to see their force and weakness. So first, what model can be used? The straight carapace length SCL can be modeled with function describing the growth of organs. The Gompertz model is a typical model to describe the growth of organ or the growth of tumor, for example. In this model, the equation is shown at the left. It is not the most important. The most important is what the parameter can say from a biological point of view. And in this model, the parameters have direct biological interpretation. K is the hatching size, Y0 is the size at laying time, or equivalent size for SCL, and A is the growth rate. If you model the progress of development using linear function, the equation is just at the left, very simple equation, but in this case, the R value has no direct link with biology. This is parameters that we need, but we cannot say really what it means in terms of biology. Now we model the growth of embryo, but we know that the growth rate depends on temperature. So we must include the temperature in the two previous equations that are recalled here, Gompertz at the left and linear model at the right. In both models, A is a measure of rate of change of embryometric, and it must be a function of temperature. So the A value must be as a function of temperature. In literature, we have several models to describe how a biological reaction can be changed according to temperature. I choose this one because I like it. This is an equation that is deeply anchored in thermodynamics. It has been published by Schofield, Sharp, and Magnuson in 1901. And this equation is, when you look at this equation, it looks like a complicated equation. But look rather at the shape at the right. It has more or less a bell shape. It is very low at low temperature. You have an optimum at intermediate temperature, and it is again very low at very high temperature. This is a typical shape for a biological reaction. At low temperature and very high temperature, you have sublethal effect, and it has an optimum at intermediate temperature. You can use any function with similar bell shape. I have no problem about this. The importance is that you must have an equation that can be changed by the value of the parameters. The value of the parameters, here we have four parameters. Rho, delta H A and delta HH, and T half H. Depending on the value of this parameter, we search to predict or the correct straight carapace length of hatchlings at the end of development for Gompertz model, or the value of 1 for progress of development at the end of development for a linear model of progress of development. We will use a Bayesian model with Gaussian distribution for SCL or the value of 1 for progress of development, and let's see the two. Look at the results. First, we fit the growth of SCL, of embryo, of carita, the logarith turtle, and at left you have the thermal reaction norm of SCL growth. You see an increase of the curve, which describes the rate of growth of embryo, depending on the incubation temperature, and the histogram at the bottom represents the diversity of temperature we had in the 20 nests that we used for this model. What you see is globally an increase, and at the end you see that uncertainty increase just because you have very few incubation temperature at high temperatures. This is interesting because if you do the same graph with maximum likelihood, you will see a decrease of growth rate. This decrease in maximum likelihood can be seen as an artifact. In Bayesian model, it is rather an uncertainty. At right, you have an example of growth of embryo within one nest. In green, you have the temperature recorded in this nest. The straight line black at the top is the expected hatchling size, and the dot blue lines, horizontal blue lines, are the different stages which are located based on the size of embryo. You see that you have growth of embryo, and the embryo, the model predicts relatively well the size of hatchlings. Now we do the same with the linear model. With the linear model, we model the progression of development from 0 to 1. The thermal reaction norm of progression of development is shown at left. It has approximately the same structure than the thermal reaction norm for SCL growth. What is different is at the right. At the right, you model the progress from 0 to 1. This is a linear model, but it does not look like a linear model. It is linear only during a very short time, but the slope of this linear model changes according to the temperature. So globally, it does not look like a straight line, but locally this is only linear models. In this model, you cannot locate where are the embryological stages. The embryological stages are defined by or structure of the embryo or the size of embryo. Here, you don't have the size of embryo, so you cannot locate where are different embryological stages. In conclusion, we have shown how to model the development of a turtle in field considering the variation of temperatures. We use two metrics, SCL size with a Gompertz model of growth and the progression of development with a linear model of growth. When you use SCL size, you can predict the position of embryological stages, whereas it is impossible when the progression of development is modeled. This is a clear limit of this way to model the development of turtles, and we will see that it has consequence when we will try to locate the thermosensitive period for sex determination. Bye.